Hello and welcome to the 14th video in this series. My name is IB42 and we are going to play the wide instructions level, or rather have a look at it. Create a device that saves the program output on even ticks and outputs both bytes on odd ticks. Save on even, output both bytes on odd ticks. It's not going to be that hard. We can use a delay line for this, right? We should be able to use a delay line. So we're supposed to output both. Where do we put the... like this should work. Save on even, output on odd. This is correct. Alright. Is there any way I could... No. It's gonna be like this. So, when do we output on odd? So that will be this one, right? I guess the first one is the zeros. Which actually makes a lot of sense. Alright. Okay, this is the first tick. We save. Wait, why is that wrong? So this is the first, we save. No, we output both. Oh, interesting. How is that wrong? We save. And then we output. There's a mistake that output both. Oh, because I have no counter. This is the problem. Oops. That makes sense. Here we are. This should solve it. Now, widespread instructions. What did we... Programmable memory component. Didn't we already have one? This is the program. This is a programmable memory component. There's a difference, I guess. Alright, while instructions. Finally, it is time for you to start the LEG architecture. And I'm going to tell you this once more. Lag is a lot of words. I found it to be very interesting when I first found out about that. Blew my mind, seriously. Because it's a lag in the widespreads actually existing architecture that shapes a lot of devices. It's called ARM. Alright. The lag architecture is a computer that takes 4 bytes per tick from the program. The first byte, which accumulates into 8, 32, right? 16 times 2, 32-bit. 32-bit architecture is what that means. 4 bytes per tick. Ticks are measured in hertz. The first byte describes the operation called opcode. Since many operations take 2 arguments, like add or, the second and third byte of our arguments. Alright. Since most operations return 1 result, the fourth byte is for the results. It's defining the result address, memory address, registers, counters, input outputs. Okay, and then we have the arithmetic engine. The opcode is flowing directly into the arithmetic engine. Maybe we actually want to take a screenshot of this. I remember, oops. I remember wanting to see this when I first played this level. Yeah. Opcodes. Flows into the arithmetic engine, whilst argument 1 and argument 2 address memory locations, which are then fed into the arithmetic engine. Blue defines the result address, and the arithmetic engine returns a result. Feeds it back into our memories slash input output slash registers. Okay, so next. The following steps, the following are the step-up steps that need to be done in order to complete this level. Click the schematics icon and create a new empty architecture. Place a programmable block with 4 outputs. We already have one, right? Anyway. place a counter, set it to increment, set its increment to 4, connect it to the program block. Add 6 registers or custom components with registers. Click Edit Link Components on the program components and connect registers to 0 to 5. Connect the counter to 6 and output to 7. Alright. Finally in this level, can I resize this? No. Finally in this level, the opcode is always 0. This means we add argument 1 and argument 2 and save the result to the destination. The value of the argument or destination refers to one of these places. Register 0, 1, 2, 3, 4, 5. 6 is counter, 7 is in out. Which is basically the same as an overture. In the next level you will implement more opcodes, which will require a different ALU than that of overture. Alright. How do we do this? Or rather, do we even take a screenshot of this? Guess not. I can remember that. Alright. This is overture. Isn't it beautiful? I love it. I really think this is a beautiful computer. Right. First of all, switch schematic. We call it NEG. We actually call it NEG architecture. So what does they want from us? Let's actually have a look at the RAM. Load save address, save value. You know, we are actually quite free to build our architecture in a way we want to, right? So, and I remember doing this, maybe I'm going to show you, because 6 registers is not that much, to be honest, and I wanted more. I remember trying to utilize a RAM component to have more registers. Actually building a custom register component using more than 6 registers in iGuessVia. We'll do this as well because 6 registers is actually not that much, and it would be great to have more, even though the level only demands 6. But I'm gonna show you a thing. See, there's this link component, right? And the level asked us to link the registers that we are going to place. Well, that's 16. to the registers. We are going to go with 16 registers for this one. The level asked us to link the registers to the program, right? And I feel like this might be a little bit confusing. So we are going to have a look at the maze. Right, automatically skips to overture, apparently. And we're going to recognize that there are, and maybe if you play the game yourself, you might have realized this, this program block. I don't even know if it was there before. Oh, interesting, look. We have a unlinked register. Register 1 wasn't even linked. So, what this does is, right, we see here the link components, which is called custom out, and the other ones are called custom as well. We monitor the output. Is that really true? Let's have a look. Yes, we actually do. So we're going to go with 14, I guess, because I feel like, yeah, or maybe we're only going with 12. No, 14 it is, since we can display the value of the counter as well. Let's have a look at this. We have output and custom components, and if we now, because we're free to do so, every component that holds a value has a, like usually every component that has a way to store a value has a linkable component. And now we can see that we can display our count as well. And if we actually play the level, we can see that we not only display the value of register 0 on top of our custom component, and since we are going to use custom components a lot more from this point on, this makes sense. There's not only a let me finish the sentence. Since we are going to use custom components a lot more from this point on, our register has a component. We can look into the component factory, right? And we can switch to schematic. By the way, if you haven't played the game, haven't had a look at this so far, custom component has a memory probe, right? And this memory probe has a link, and this memory probe creates a linkable component for the custom component in our level. If it wasn't there, we wouldn't have been able to link it to our program. Right. Back to what I just told you. The 2 is displayed on the custom component, since it is the value that we are immediating from our program, and it is displayed not only on the register but also in our program, which comes in very handy. See, we can also display the value of our counter. Yeah, enough of that. I guess this is understandable. Back to this level. So what did I say? I said we were going to use 14 of these, right? Let us do so. These are 4, 6, 7, 14. And we're going to use counter. We might actually build a custom component out of these. Might actually build a big one right from the start. Having 32 or even more 64 registers to address. I guess let's actually do this even if we are not going to be able to use this. Let's go with the 32 bytes register. It's gonna be handy anyway. Six, 9, 12. Sixteen. Let's see, we should be able to create probes for these, right? Memory probe, wire probe, memory probe. We are going to use the first 14. No, actually how many are these? Can we see it? No. Oh, it's actually we want to be able to display all of them. So we are going to make this thing a little bit bigger. We just deleted 12. See, the way the component is created is each one of these blocks in the raster will create one block of custom component size. And this is why we build it like this, so we can display all of them. 1, 2, 3, 4, 5, 6, 7, 8. Perfect. Creating it like this lets us... Oh no, it's gonna be a problem. It's gonna be a problem actually. because these will overlap. It is possible to display single-digit numbers that will just overflow and they will be unreadable. We actually want them to be readable. I'm gonna have to space it even more. For it to be nice. I actually maybe want to build it in a way that it will be scalable by copy pasting it. If we want a bigger register later on. So that would mean now we have 8. This might actually already be fine, but we are going to space it even more. So we will have enough space to display the numbers no matter what. So for all of this is just able to work with. So how do we want to do it? Probably like this. Connect the probes. Yep. Building it at a scale, building it in a scalable manner will enable us to upscale it if we will ever want to. And not only that, it will also this is what I wanted to tell you about. Since for now we only save like this is a byte, right? This is 8-bit. Whilst these two in combination would be 16-bit. Whilst these 4 be 32-bit. Maybe we actually want to go, oh no, never mind. We don't want this, we get bigger components later. Forgot about that. This is just bytes. Yeah, we might want to deal with larger numbers later on, like 64-bit. And we could actually build a custom component that was able to do so. We'll unlock these later though, so just remembered that we don't have to build a custom component, but we could. And I guess this is worth mentioning. 64-bit are able to display way larger integers than just 8-bit, right? I hope this makes sense. And even 9-bit would be able to display the double amount. It scales upwards crazy from just 8-bit. Scales like crazy. Alright. Back to building this component. We actually want to have two bytes of inputs. Did we link all of these? No. I guess we did. Yes, we did. The numbers are showing. Oh, this is not a clear. Way of doing it, or way of checking. So this is actually interesting, because this stuff is going to be actually nice. See, so far we have this is a 3-bit decoder, right? Gives us eight possibilities. We can use this decoder to build a tree, basically. Don't remember how to do this. I hope so. First of all, I mean, this is gonna be enough for now. Still wanna do it. Okay, we've hit the 30-minute mark actually, and I think that this might actually take a while. So I guess I'm gonna end the video right here and leave you with this. Sorry that we didn't make it so far. Maybe I'm actually going to start to cut these videos, because I mean, all the things that I just told you about, I hope they're interesting to you, but yeah, it takes a while. And I'm rambling, sometimes I'm building, not saying anything. Let's see.